Any questions? So I have a question about Poisson's ratios.
Right.
I think I saw one sample that had like a Poisson's ratio of negative 0.3.
Right.
I was wondering from like all your different designs, what was like the most extreme Poisson's ratio value that you've seen? Just like really curious.
That one is also extremely very possible for anisotropic property. For anisotropic, even 100 is also possible.
Okay.
Right. For isotropic material, we have some value, right? -1 through 0.5, right?
Right.
But anisotropic, no boundary.
No bound. Oh,
Right.
I see. So you've seen like negative 15
Right.
or something?
Right.
Oh, okay.
Very good. So this one is also anisotropic, fraction dependent, right? So Poisson ratio is also no boundary.
Oh. Any other questions? All right. Well, thank you so much.
All right. Thank you.
So our next speaker.
I'm ready.
All right. Is there a sheet? Do they print out the top?
Yeah, if you don't have a
Oh, I tried to get the app working. Let me try again. Try to get the app working, but did it require a password?
No.
Oh, okay, maybe I'm on the wrong app. Okay, maybe I'm on the wrong app. Oh, okay, I scroll down, right? All right, so our next speaker is Dr. Lee from Northeastern University. Maybe I'm not reading the right one, sorry. Wait, I'm not reading the right. Okay, so, apologies. Dr. Imani from University of South Carolina, and the topic is on thermomechanical architected materials, paving the path to future Venusian flights with vacuum airships. Looking forward to your talk.
All right. Thank you. Hello, everyone. Today I talk about a project we have done for NASA. And in this project, we studied the feasibility of developing a vacuum airship for Venus exploration using Bouyant architected materials. As you know, Venus is a hot planet. The pressure over there is very high. It's crazy. It's like almost in kilometers under the water. The atmosphere is like very acidic, corrosive, and the density of the atmosphere is very high. So it's a tricky place to go, not easy. 30 years ago, Soviet Union sent Venera 13 to Venus. It was a lander, and it lasted about 2 hours before it get toasted. But the time have changed, and NASA is sending Da Vinci next decade, and the duration of the mission gonna be about 20 minutes. The problem is still there. It's a big challenge. There are a lot of proposals how we can go there and basically how we can kind of last longer over there. And most of the ideas are about putting all the scientific instruments within a chamber, and you're going to provide some cooling so you're going to last longer. In addition to this, there are you can use some chemical fuels. With that, you can kind of last several days. Also, there are advancements in science. There are silicon carbide electronics. You don't need really much environmental protection. And when it comes to mobility, most of the ideas are about using an airship. So assume that we have this system over here. We have our cold bay in the middle, and we have an envelope around, and we have this gray space in between. So the easiest way just comes to mind to make it mobile is to insert some lifting gas in this gray area. So it's going to definitely provide us the mobility, but where's the problem? It starts circulating the heat over there, so we're not going to kind of get or satisfy the thermal requirements. So how about the idea if we replace this lifting gas with some sort of kind of spare solid, which are going to call it Bouyant architected materials or bands in this presentation. If we do so, this band needs to basically satisfy some requirements. So we need some kind of physical requirements. It should be buoyant. It should be sustainable. It shouldn't react much with the chemical composition of the atmosphere. We need low thermal conduction, low radiation, and also it should be very strong. We should take that crushing pressure of the atmosphere. And not really many materials can satisfy requirements simultaneously, but there's one specific category that I want to talk about, and that's the ceramic materials. So, what do we know about the ceramic materials? We know that they are brittle, but the question is that is that always true? So to answer this question, we need to think a little bit more about the fundamental of the materials. We know that their strength is pressure sensitive, right? So at low pressure, what we see is kind of brittle type of material, and this is what really is what we expect. But as the pressure increases, the strength increases, and what we are getting is some sort of plasticity as a failure mode, right? And there are a lot of kind of constitutive models that can capture this kind of behavior for us. One of the most famous one is extended Moore column model. So what you may ask me that, okay, how can this help us in designing of the bands? I tell, well, assume that we have a stretching dominated translators material under the state of the hydrostatic pressure. Ideally, we have the state of uniaxial compression between the strata. So having this, we're gonna have the relation between our shear and pressure, which is gonna be this dashed line. So if we follow this dashed line, we're going to keep this curve. And what is this curve? This is the extended Moore column behavior of the material. And what is this point? This is basically the theoretical strength of the material within the lattice. Okay, how does it help us? So we are looking for kind of like a proper choice of the material to identify, okay, what material is good for our design. So we can take a look at the, for example, different properties of the proper popular kind of ceramic materials to see that which one kind of fit our kind of like design. Here we have strength versus the density of the ceramic terracotta material at their theoretical limits. What we are looking for is very strong material and very lightweight. So we are saying that silicon carbide is an outstanding kind of candidate here. So very strong and very kind of like low density. Low density, what we have is kind of like high kind of lifting power and lifting capacity. Well, you may tell me that, okay, take a look at here, the thermal conductivity isn't that good in comparison with other ceramic materials. I say that, yeah, you're right, but this is not the whole story. What you're seeing here is the property of the ceramic materials at room temperature, not Venus temperature, which is 500 degrees C. The unique thing about the silicon carbide is that it can save its mechanical properties at 500 degrees C. It doesn't create that much elastic modulus strength. And the good thing, or good news, is that the thermal conductivity of silicon carbide decreases a lot as the temperature increases. So this is what we are looking for. As a result, this is a kind of promisable kind of candidate. At this stage, we use this one as a kind of parent material of our design. Also, we use Kelvin architecture as the kind of like architecture of our lattice. So may I ask you that, okay, so is silicon carbide Kelvin kind of silicon carbide Kelvin lattice manufacturable? The answer is yes. Some experts have shown that we can develop high quality, high strength silicon carbide Kelvin lattices. So if we are using silicon carbide, we need to keep the relative density of our lattice below 2% to satisfy the buoyancy requirement, right? And we know that at the theoretical limit, the relative density of the lattice is 0.34%. So there is a very nice gap between 0.34 to 2%. We just search for different designs. Okay, before going to the design of the BAMs, let's kind of like develop some analytical formulation for strength scaling of the ceramic terracotta material to make it easy for everyone to use. Basically, the traditional Gibson-Ashby type relationship that we all use, and this is basically kind of a linear kind of relation. We have like the strength of the material here, which is a constant number, and the relative density of the lattice, and which is going to be like this line. Okay, if we substitute this like strength term with like the external Moore column kind of like behavior of the material, we're gonna get like this expression, which is a function of the still relative density, and we have the state of the pressure within the lattice. What is the state of the pressure inside the stretching dominated transverse material under the state of the hydrostatic pressure? It's going to be the ratio of the pressure of the environment over the relative density of the lattice. Right? Substituting this here, we're going to get this expression, and we can use it as our new strength scaling relation for ceramic transverse material. And this is this here. You can see that we get huge advantage as the relative density decreases in comparison to what we have traditionally. So if we do a two-term power law feed to this kind of analytical formulation, what we are getting is a combination of linear and non-linear term. And linear term is what we are getting like kind of like at higher relative density, and we are approaching like the traditional Gibson-Ashby kind of equation. And the non-linear term is what we are getting the most advantage kind of at low relative density. And later on, I'm gonna just use this one to just kind of validate our numerical results. So let's do some simulation. We pretty much did everything here, like three-dimensional elements, very boundary conditions. We had a lot of stress gradient on the surface to get like accurate, basically, stress on the surface. We use these membrane elements. A lot of mesh convergence for like a model with 1% relative density. On the upper side, you're gonna have like 1 million elements. So, and what basically these models provide us, they kind of provide us the kind of tensile and shear stress distribution within the lattice. And these are two of the failure modes that we are kind of studying in this project. In addition to these two, we need to just take care of the kind of like buckling too. So what we found about the Kelvin lattices on this, under the state of the hydrostatic pressure is that their critical buckling wavelength is linear than the periodicity of one unit cell. So we need to at least have 2 by 2 by 2 tessellation to capture the critical wavelength. So the other type of analysis we can do is basically thermal conductivity analysis. This is just kind of less exciting in comparison with the previous one because this is not really much geometry dependent. You can easily capture it using this kind of analytical formulation, which is for Kelvin lattices. But important, we are at 500 degrees C. Conductivity is important, but radiation is more important. So if you have researchers shown that the silicon carbide lattices can have a lot of kind of these thermal effects at high temperature, and these kind of like yellow bars show thermal effects in comparison with the conduction. So to take care of that, we can use this analytical formulation, which kind of include, which is for the Kelvin unit cell, which include the effect of the cell size, relative density, optical properties of the material, and also temperature. So, having all these tools, let's investigate some baseline cases to see that at this stage if like the idea of the BAMs are possible or not. We consider two baseline cases. We have these BAMs with hollow struts. The kind of sizing criteria is the optimality of the buckling within the struts, which is going to be the smoothness happening of the Euler and shear buckling. So we check it for these four relative density, 2%, 1.5%, 1%, and 0.65%. For these designs, we can see that we have like very high buckling factor of safety. They are very good. Like in shear, some of them perform good, some of them not. In tension, they are awful, not working good. So going to the second category, which is the BAMs with solid cross-section struts, you see that we have excessive tensile factor of safety, good shear factor of safety, but they are not performing that brilliant buckling. So, but still two of them, you can see that for all three failure modes, we have factor of safety greater than 1. Okay, so we have this understanding the idea of the BAM, the idea of the vacuum airship using the BAM is possible. So let's do some optimization to see that how we can kind of like improve this numbers or factor of safety, right? So there are like, we do optimization for kind of like BAMs with hollow cross-section struts and for solid cross-section struts. And there are basically like hundreds of ways you can do that, just no limitation for that. What we have done is we use like two parameters, A bar and R bar. A bar is basically distribution of the cross-sectional area along the length of the struts, which is basically kind of responsible for tuning of the stress. And the R bar is the distribution of the radius of the struts along their length and in hollow cases. And this is mostly kind of like responsible for tuning of the buckling. So we use this kind of set of intuitive functions to make these kind of like parameters. And for hollow cases, we totally have 16 design variables, and for solid BAMs, they used 8 design variables. Again, like 100 choice of the optimization algorithm, we use covariance matrix adaptation evolution strategy. We do different optimization. This is a sample of optimization, which the objective function is the ratio of the relative density over the factor of safety. You can see here the evolution of the profile of the strut. Here you see the evolution of the objective function in different generations, evolution of the relative density, and evolution of the factor of safety. And this optimization ended up in a design with relative density of 0.65%. So let's take a look at like the result of this optimization. You can see the distribution of the A bar, R bar, the profile of the optimized kind of design. And here you can see the tensile stress distribution between the lattice. And you can see that between the struts, we have pretty much uniform tensile stress distribution. And this helps us to get factor of safety greater than 1 in this lattice. Going to shear, we have huge shear concentration between the nodal regions. But this is what we expect, right? Translattice material, this is like the nature of them. In nodal regions, they just experience kind of stress concentration, nothing new. But here is the beauty of our work. So we have shear stress concentration here, but we also have high pressure in the lattice nodal regions. We have high pressure. What does it mean? We have high strength here. So you can see that this kind of secret sauce help us to get factor of safety greater than 1 even for shear, right? And the kind of like buckling of the lattice, the strength that we are getting is greater than the pressure of the atmosphere. So let's take a look at the summary of the optimization results. We can see that for the solid kind of BAMs, we are getting 5% improvement over the baseline cases. Very exciting. You may ask me that, okay, what is this kind of like 5% cutting edge number means? It means that the optimization wasn't successful. We didn't do anything. So it wasn't successful for solid cases, but for hollow cases, we get like really good numbers. And interesting, you can see that all the 3 factor of safeties are equal for the optimized results. And they happen simultaneously. And this is basically show that the optimization was pretty much successful, right? More interesting, you can see that as the relative density decreases, we get huge improvement over the baseline cases, right? And why does it happen? This is just a simple example. Before optimization, this is the baseline case. We get like, this is stress distribution. We get like compression, tension, a lot of like gradients. After optimization, we have more uniform distribution. So this helps us to get like these numbers. And you can see at like lower relative density, we get more than 6-fold improvement over the baseline cases. Comparing to the theoretical limit, you can see that again, as the relative density decreases, we get kind of approach to that kind of theoretical limit. So here you can see the profile of the optimal design with different relative densities. On the left-hand side, you can see the corresponding strength here in the red dots. And you can see that they are, here we have this solid black line. This is a traditional Gibson-Ash-type equation that we had. And this kind of like dashed black line is the basically analytical formulation that we developed. You can see that the numerical results are in the vicinity of this kind of analytical formulation. So the optimization was pretty much successful. Maybe the most important part of my presentation is this side. So this is like the kind of scaling relationship that we have. This is the general thing or linear kind of like a scaling relation that we are using. If you write our analytical formulation in form of this, you can see that the kind of beta is going to be 0.48. And if you do a one-term kind of like power law feed to our numerical results, what we get for beta is 0.62. If there is one finding that I want to communicate to you in this slide, it's going to be the fact that the ceramic terrestrial material can achieve better than linear strength scaling. And this is exactly what you're seeing here. So we did also imperfection sensitivity analysis. We found out that hollow BAMs and low relative density and also solid BAMs, their tensile factor of safety is very sensitive to imperfection. At high level of imperfection, they cannot really scale the factor of safety greater than 1. So the last thing going to be the kind of thermal properties. These are the results of the kind of thermal conductivity analysis. We can see that they are pretty much low, but no surprise, we expected this, right? But you can see that, like here, the kind of the thermal conductivity of our thermal conductivity of at very low relative density is even better than the silica aerogel, which is like silica aerogel is like very good thermal insulator. But this is not the whole story. If we add the effect of radiation to these numbers, you can see that we get like effective thermal conductivity, and you can see that these are not anymore kind of small numbers. This is still good. In a couple of seconds, I'm going to show you a kind of lifting gas like helium, and you see that these numbers are not that bad. But we can easily modify that. We can apply some low emissive coating on these BAMs. For example, we can apply for like electrode deposit some gold, and these are going to be the numbers that we are getting. So comparing with the lifting gas like helium, you can see that in the worst scenario, the BAMs can provide us 10 times better thermal insulation performance in comparison to the lifting gas like this. Okay. So summary, we just showed that the idea of the vacuum airship using BAMs is feasible. So we developed analytical formulation, numerical results, and confirming that we can reach the ceramic terrestrial material can achieve better than linear strength scaling. We realized 62% of the theoretical maximum strength, 70% of the buoyancy, and also we show that the thermal kind of like properties can improve a lot. Thermal insulation properties can improve a lot. Thanks to our sponsor NASA for funding this project, and thanks to Andrew Gross, who is my advisor and is an assistant professor within the mechanical engineering department of the University of South Carolina. And all being said, if there's any question, I'll be happy to take it.
Good time, good time. Yeah, questions? Yeah.
Can you go back to your slide where you introduced your optimization, please?
Sure.
Yes. Next one.
Uh-huh.
Right, so I found it very strange that they all converge to the same factor of safety. You were using that as your objective functions, right?
No, the objective function is going to be the minimum of these three. But the end, like the optimized design, it's like basically the definition of that's what I call the definition of the optimality. When all the factor of safety that we have like happen simultaneously, like the things that we say in like a bucketing. So when kind of like bucketing of the column going to be optimal when we have like the simultaneous shell and under bucketing. But if you're asking about what was the objective function, it was relative density over the factor of safety. It was for unconstrained optimization. These things that you see here are constraints optimization. I didn't mention this, but right now maybe it's a good opportunity to talk about that. Here, kind of like this is an unconstrained optimization. You can get a data-driven platform because they are super expensive. Like kind of optimization takes more than a month to be done. So we can kind of like get a kind of data-driven platform. We can use these points as the next start point for the constraints optimization with a target relative density. So it makes it kind of like cheaper. So, but about your question, this factor of safety is minimum of those three. But at the end, when you kind of like see that, okay, what your optimized design, you see that, okay, all three factor of safety are equal. Like clear yet?
So are you saying you only had one objective that you're actually solving for? Just the lowest factor of safety of those three?
Yeah, for example, I analyze the models. Okay, I get like one factor of safety for bucketing, one factor of safety for shear, and one factor of safety for like tension. Which can be the critical one, the lowest one. So
this wasn't necessarily like a multi-objective optimization.
No,
I'm
gives you
kind of
problem.
curious why you used an evolutionary algorithm. Because I just felt like gradient-based method might have been faster. I don't know.
Yeah, that's a good question. So
It worked.
yeah, they work, I know, but like, yeah, maybe at that time that we were doing this, we didn't kind of like consider that one, but it can be used, yeah.
Great work.
Thank you.
And I have a question about the factor of safety. So typically, like, you have an application and there's like a set factor of safety that must be met. For, I think this is a space application, what is a typical factor of safety? Is it 1? Is that right, 1.4?
So factor of safety one means that it doesn't, it's like in kind of exactly the same whether it fails or not. So we need basically, typical like ruling then is like, well, like 20% more than that, so.
Oh, it's, okay, I
And
see.
basically what I show was that they are kind of, some of them are like, at least lower density, they are kind of like imperfect. They are sensitive to imperfection, so kind of not really much manufacturable. Like maybe the most reliable one is like this 1.5% or like something in this range. So.
Yeah, because the higher you go, the heavier everything gets, right? So.
The lifting power decrease, yeah,
Right,
as far as.
so there's gonna be, so you wanna just meet the, minimum, alright, thanks, well, I mean, question, yeah, one more question.
How did you, how did you obtain the thermal conductivity?
It was
You
like,
simulate?
yeah, for like thermal conductivity simulation, so, but for radiation, no, we kind of use that kind of analytical formulation.
Oh, analytical what?
Analytical formulation, I said.
Formulation, like a simulation.
For radiation, we didn't do simulation.
Okay, what about conductivity?
We did formulation for that.
Can do that. Did you do that?
Yes. This was like the conductivity kind of,
And
you apply basically the thermal kind of degree of freedom on your periodic phases, so you have your hot phases and cold phases.
Then effectively, how
So like basically,
Alright, great, thank you so much.
Yeah,
And
sure.
next speaker is